Welcome back. Today in this lecture, we are going to continue our journey on understanding meshing in OpenFOAM using SnappyHexMesh. However, in this lecture, I am going to show that in what kind of meshing the SnappyHexMesh finds it harder to mesh, and what other tools are there that are free to use, the open source, and that you can use to create good quality mesh in those cases as well. Let's get started. We'll start with creating a cube, and for that I'll just use these few points starting from the origin, which is negative 0.05. This is negative 0.05, negative 0.05. This is the first point. Similarly, 0.2, which is equal to, so let me copy all these. So we need 8 points for a cube, and let me directly write here x max is equal to negative 0.05, so that we can change it. X min is equal to 0.05, y min is equal to, so all these are also same. Let me make it 0.1, 0.1, and so on. Now I can use those points here. Min, this is y min, this is, let's change this from x min, I'll change to x max. Let me use only 4 points and then I'll extrude. That will be much easier. So I'll just use x min here, then x max, z max, and then x max and z max, and then x max and z min. So using this, I can create this. I think there was some problem in the script. We have missed these semicolons here. Now let me open this. Now I have 4 points. I can connect them to create lines and then surfaces, and then I can extrude, translate. I want to translate in y direction, which is negative 0.1. We'll see whether this is correct or not later, and then select all these 4 points, press E. So now we have a decent looking geometry here, and now we'll create surfaces. There are 4 existing surfaces. I'll then create one here and other one here. Once this is done, I'll get everything here in the script. Clearly this should be 0.2 and y min is negative. Let's make this in the positive direction, and now let's reopen this and then create a 2D mesh and then export this as triangle. So we can do this by our command as well, like this, and then move this triangle.stl to try surface. And also let's visualize this. So I'll just create blockMesh first and then open ParaView. Here is the block, and let me open the surface, which is here. Clearly it's way outside the block that we had. Let me create the block such that this particular object is enclosed inside. Then only SnappyHexMesh will work. For that, I'll go to blockMesh and change these values. It starts from negative 0.8. Let me make this 0.5 and go till negative 0.2. Let me make them positive first and then 0.5. And in the y direction, I want more number of points now. So let me add say 10 points along y direction. Now again run blockMesh, and then let's observe. Here we have the block, and now let's open the try surface, which is not visible now, so I'll change this to wireframe, and now you can see that it is completely enclosed. And to make this little bit better, I'll change this. In this direction should be y min is in this direction, it's negative 0.1, so extrude is in this direction, which looks okay. Let's see how the mesh is created for this. The script that we are using for SnappyHexMesh is same as we have used for 2D cases. I'll remove this because this is not required anymore, and then this one is already commented. Now I'll just use the script that we had before. Let me show you the script as well. It will remove all the existing created features as well as the mesh. Runs blockMesh, then surface feature extract, then SnappyHexMesh. Surface feature extract, we don't need this large angle. I'll keep this as 120 and then run. You can see that 97% of the boundary layer thickness has been created, and let's observe how it has been created. From the outside, nothing is visible. Here there is something. Let's look at one of the slice along z direction, so you can see the block here. Now here, if I just directly observe this, you can see that here there's some nice looking layers, and as you can see in this, in here you can see that it created all the layers that were requested. And then let's also look at this option, which is crinkle slice. In crinkle slice, the mesh quality, the mesh that you want to observe, looks much better. I'll look along the z direction. I'll change this to 2D, and now if you just look at the mesh, you can see the mesh layers have a better visualization compared to what we have seen before. Let's also look at the surfaces only. Let's just look at the surface of the cube. You can see that the mesh is very good. The edges are nicely resolved and everything looks good. Looks like the SnappyHexMesh works very well with this kind of sharp geometry. But here is the truth, that it does not. The fact that it worked here very well is because this particular geometry is aligned with the Cartesian grid. Since it is aligned, it was able to resolve this with a very good accuracy. But if I just rotate this particular geometry by a little bit, let me rotate this and again do this. In order to rotate, you can again just do this. I'll just go to this Gmsh and open triangle.geo. We are going to edit this triangle.geo file. I'll rotate this, transform rotate about y-axis. My axis of rotation is this, my angle is this, and let me choose any 4 lines just for the illustration. Press E, and you can see that it has been rotated with some angle. Now I'll just re-edit this. This is how it is being rotated. I'll change this to here and then change curve 1, 2, 3 and 4. Again opening this, you can see it is still a square, but it is rotated. Now if we just look at the geometry with the blockMesh here, I'll open this. Let me first create the geometry, again to STL, and then move the triangle to the sky surface folder, and then open ParaForm. Here I'll also open the tri-surface file, and now this is a wireframe. Here you can see that along Y, unlike before, it is not aligned to the Cartesian grid. So now I'll just run this. The geometry has not changed at all. Therefore, we should expect that the mesh that it is going to create will be good as before. First of all, we'll observe here that the layers were not created with very high accuracy. Not all the layers has been created. As before, we requested 20 layers and we had 20 layers, but we have only 3.8 layers. And here, if you also observe with edges, let's take a slice of this along Z. Here you can see the mesh layers are not fully developed, and along the corner they are not developed at all. And here you can see that there is a bit of a overshoot. It goes into the surface. We will also observe how the surface looks, but let's also observe a slice along this axis like this, and here we'll also look at the crinkle slice. This should be along the x-axis. Let's look at the 2D version of this, and here you can see that the layers has not been created, and it looks like from this slice as well that the mesh went into the surface. So now we'll look at the surface. Go here and switch off this and switch on this. It will just show us the patch, and if we zoom into the patch, from this point you can see that the edges are not snapped properly, and here also you can see the corner is not snapped properly as well. Now we'll talk about the actual process of creating this particular mesh, and we'll see that what different can be done, and it is done in another open source that we'll discuss in a short while. I'll set this to false and this also to false, and then create a mesh. If you open this now, from the outside it looks like the mesh is same as before, but if we just look at the surface, you'll see that it is a bunch of jagged edges. And if you look at the surface mesh, then you can see that it has created very good mesh on some of the surfaces which were aligned to the Cartesian grid, but since they were not aligned, they, in the castellation stage, it just created the requested mesh size on the regions that we have selected. For example, we said that near the feature this should be the mesh size, and on the surface this should be the mesh size, and so on. The next stage after this is snapping. What snapping does, it tries to move the points which are close to the surface, or for some of the cells it will chop it off. This process sometimes create a cell which is wrongly projected to the surface instead of the edge, or vice versa. It should be projected to a surface, but it got projected to an edge. Now we'll look at the next stage, which is snapping. If we set this to true, then we will see that here we'll have the same problem as we have seen in case of the previous mesh. Clearly the problem is with snapping, and you have to either write your own implementation for this, or you have to move to some other open source tool that we'll discuss in a short while. Here you can see that it looks like it is correctly snapped, but if we zoom in, you'll see that near the edges we can see the problem. Let's look at surface with edges, and you can see there are some snapping which were not correct, and that caused the problem. And if you run the check mesh command here, it says that mesh is okay. So sometimes they tell you that the mesh is okay, but as we have seen here, that on the surface the actual geometry was not captured accurately. So if that is the case, then it is actually not suitable to run the simulation on this particular mesh. So you should take care of these things. So these are just the indicators. They tell you that the mesh is okay. Whether the mesh is good for the simulation or not, these indicators do not tell you that. So now we'll talk about another measure which is also an open source. It's called CFMesh, and if you install this, then you'll get these measures, which is Cartesian mesh and PMesh and various others. Now what we are going to do is we are going to write a minimal dictionary, so you cannot use this same dictionary for this particular solver as well. And also, to create a mesh around this particular geometry, which is here, triangle.geo, you also need the outer domain to use this CFMesh meshes. Therefore, we'll go here and create another domain outside this. Let me again do all this, which is first creating the domain. So I'll create a domain from -1 to 1, and the mesh size I'm going to keep as 10 times of what I have chosen previously. Here it was 0.05. Let me choose 0.5 here, and then follow all these steps. Here it will create 4 more points. I'll, for safety, start with point 10, 11, 12, and 13, and then I'll go to Gmsh, open this. Now you can see, I think we missed the semicolon here. Again, open this. Now the problem, I think 10 is also present. That's why it's showing the error. 10 already exists. Let's make it say 15, 17, and 18. Let's try this. So these are the 4 points. I'll again use this add line and then extrude this. Translate. I want to translate this along the negative y direction. This is -1, 0. So -2, because this is already at -1. And then I'll select these 4 lines and press E. Now I'll create the rest of the surfaces, and similarly this one. And along with this, the CFMesh mesher also requires labels. So I'll create labels, create physical groups, add surfaces. I'll add these 4 surfaces as outer, and this one as well, and these as inner. So maybe there was some problem. Let's see what is that. It created this. This is one problem. I'll remove this. So after this, it created 2 physical surfaces, outer and inner. And then again, let's open this and let's try to mesh. So it created the mesh. Looks fine. And then export this as triangle.htl. I'll select htl format here, and here remember that you have to write this as per physical surface. When you write like this, you will find that in the htl file you will have outer and another htl inner in the same file. This is how you can write a file for CFMesh. Then the second thing is you have to create a mesh dict. How a mesh dict for a CFMesh looks like. Let's look at that. The minimal setup that CFMesh requires is the name of the file and the max cell size. I'll change this to, you need not to keep this particular file in try surface folder, and here I'll choose max cell size to 0.1. Now I'll just run Cartesian mesh. No need to run blockMesh as well, and it will create the mesh for you. So you can see that it created something like this, which looks even worse because it did not capture the edges. Let's look at with the surface, but it looks very smooth. And if we take a slice of this, then you'll see that it also did not capture anything inside. So that means that the minimal setup is not that good. But there is one thing that you can do is you can extract the feature edges. So, and this is another application which comes with CFMesh. It extracts the feature edges, which this CFMesh mesher uses to make sure that it is capturing some essential features which are describing the geometry. once this is created, you have to change this to triangle.fms. So now if I run Cartesian mesh and now look at the mesh, you'll see that again not much change here, but let's also look at the mesh inside, not much change here as well, right? Now let's try to do something more. So we can define the local refinement. We have the inner. For the inner, we can define a local refinement, something like, since the size is 0.1 there, so 0.1 to 1, as you can see here, negative 0.1. So I'll choose this for the inner, and for the outer, I'll choose 0.1 as in the global mesh. Now let's try with this. Again, doing ParaFoam, you can see the mesh has improved a lot. And at the middle, if you take a slice, you can see this is also captured much better. And I'll switch this off. I'll switch the plane and then activate clinical slice to let you observe this in a better visualization. So you can see that how the mesh has resolved this properly. And let's also look at the patches. You can see the inner patch and outer patch. Let's only look at the inner patch. Here you can see that it has captured the corners very well, and you can see that this is not aligned with the grid, and still it has been captured well. There are many other features in CFMesh to create boundary layers and to create refinement zone and various other things that we'll discuss in another lecture. Thank you for listening. If you like the content of our channel, then you can like, share, and subscribe. Thank you.